goal of this learning module is to educate you, the Mason, with a code-based and best practices working knowledge of Mortar. The technical content of Mortar for Masonry is based on building code requirements and specification for masonry structures, or TMS 402 and 602. When we refer to the code in this training module, we are referencing these two documents. As a trained mason, you have a mental list of what mortar is, what it is used for, and how it is prepared. Typically, you have been taught in the field, with a trowel in hand, how to spread mortar and butter an end joint. You've been told what to do and what not to do, but do you know why? Why is this mortar joint acceptable? What mortar joints are not acceptable? We'll get back to this. Historically, individuals entering the masonry industry are taught technique, but often even seasoned masons do not know the actual code requirements for their craft. By learning to think about the work you perform in terms of building code, meaning what is universally acceptable to designers, engineers, building code officials, and building owners, our industry, your profession, can aim towards a uniformity of expectations. Every mason on a project can perform their craft with a mind toward meeting building code requirements, rather than, that's how we always do it. What is mortar? Mortar in its purest sense is a mixture of cementitious materials, aggregates, and water, with or without admixtures, that performs a variety of critical functions in a masonry wall. Mortar bonds the masonry units, joint reinforcement, anchors, and accessories together to perform as a single assembly, a masonry wall. It also creates a tight seal between units against the entry of air and moisture. There are different kinds of mortar called types. The mortar types are defined by ASTM. ASTM is one of the largest standards developing organizations in the world. ASTM establishes standards for all the common masonry materials used in America. These standards are incorporated into the building codes. Since the very beginnings of ASTM, masons have had a key role developing the masonry standards along with architects, engineers, contractors, producers, consumers, government officials, and academia. Knowledgeable architects and engineers select the weakest mortar that satisfies the structural and durability requirements for the project, because mortar with less cement provides the mason with the greatest workability. Architects and engineers want to do everything they can to help you achieve full head and bed mortar joints. ASTM identifies 4 types of masonry mortar: type M, S, N, and O. Each has different properties that are important in different applications. The type of mortar you will use will always be specified by the architect or engineer on a project. Even though the mason will never be selecting the type of mortar, as a masonry professional you should understand the basic qualities of each type and where they are most commonly used. Type M has the highest compressive strength and is the most durable in freeze-thaw applications. Its high strength creates several conditions that make it the least specified of the masonry mortar types. In its plastic state, before the mortar hardens, it has the least workability for the mason. Its stiff consistency makes it much more difficult to completely fill bed and vertical head joints. Masons must take greater care to minimize mortar smears, as type M is the most difficult to clean off masonry units. The higher volume of cement in type M mortar creates a more brittle mortar in its hardened state and has the least elasticity of any of the mortar types to accommodate slight wall movements. This can increase the potential for the wall to crack. The high cement content also makes it more prone to shrinkage cracks. Type S mortar has a reasonably high compressive strength. Type S creates wall strength comparable to type M. Type S mortar bonds well to masonry units and is considered to have a significantly better elasticity and workability than Type M. Type N mortar has medium compressive strength. Type N forms an adequate bond, has high elasticity, and is considered to have better workability than Type S and Type M. Type O mortar is a low-strength mortar usually used for restoration of structures originally built with similar mortar. Type O mortar is generally not used for new construction. Listed below is a very basic guide for architects and engineers on the selection of mortar that has been adopted from ASTM C270 standard specification for mortar for unit masonry. Understanding typical uses can help avoid job site errors of using the wrong mortar type at certain locations. It is common for multiple types of mortar to be used on the same job. Plans and specifications must list the type of mortar to be used in various locations of the structure. Installing the correct mortar is one of the most important responsibilities you have as a mason. When the wrong mortar has been used, it can put the architect or engineer in a position where they have to have you tear the wall down and replace the wall. With mortar, we have one of the few building materials where stronger is not necessarily better. One of the most important mortar concepts is that no single type of mortar is good for all purposes. We know about mortar types, but how does that affect the work in the field? ASTM provides the architects, engineers, and masons two methods of specifying a mix in mortar. One is called the proportion method, the other method is the property method. Which method to use is decided by the architect or engineer and written into the project specifications prior to bid. Even though these decisions are made before the masons lay their first unit, as a professional it is helpful for you to understand the background behind these decisions. ASTM C270 uses the proportion method as the default mortar specification, so if neither method is specified, the proportion method governs by default. The proportion method is basically a series of 16 different mortar mix designs that are listed in a ASTM C270 Table 2. The table is organized by type M, S, N, and O, and shows various combinations of cement lime, mortar cement, and masonry cement mixes that over the decades of use have proven to produce reliable mortars. The proportion method is the simplest. Unless the specifications state otherwise, the mason contractor has several mix designs to choose from for each type mortar. There is no testing required as long as certificates of compliance documents are provided, although field inspection may still be required. For example, assume the specifications simply state, all masonry mortars shall be type S in accordance with ASTM specification C270. No mention of proportion or property is made in the specification, so the proportion is the default. The mason contractor may choose mortar cement and direct the crew to mix 1 part mortar cement and 3 parts mason sand with the maximum amount of water consistent with the best workability. By the same token, they may choose to use 1 part Portland cement, 1/2 part hydrated lime, and 4.5 parts mason sand. Both methods would be considered acceptable for the specification, but only one type should be used from start to finish on the project. Mortar is proportioned by volume. When a mortar mix design refers to a part, it means an equal volume of the materials listed in that mix design. A cubic foot is the most common part used when field mixing mortar. While premix mortars that contain the cementitious materials and aggregates already blended together in the bag can be produced in the factory using the proportion or property methods. Most use the property method and require testing. The property method requires that a mix be created and tested in a laboratory before it can be used on the job site. Architect or engineer specifies the type. The compressive strength, water retention, and air content must be tested before construction to show compliance to ASTM property requirements. The mortar would then be produced with the same proportions and materials that demonstrated compliance in the lab test. Field inspection may still be required. On the job site, the mix needs to be consistently measured and mixed from batch to batch. Architects, engineers, and job site inspectors will want to see some type of measuring device used, such as a cubic foot box. Water is adjusted to weather conditions and absorption differences of the masonry units if different kinds are being used. Retempering is the addition of water on the mortar board to replace water that has evaporated due to environmental exposure. Mortar may be retempered for up to 2.5 hours after initial mixing, or 2 hours in hot weather, and depending on site conditions such as rain and wind. Mortar should be discarded if it shows signs of hardening, or if the maximum usage time has passed since initial mixing. When colored mortars are used, retempering often impacts color. As a practical recommendation, colored mortar should not be retempered. Workability is one of the most important properties of a plastic mortar before it hardens. Workable mortar means it clings to the trowel, yet spreads easily as mortar is applied to the masonry unit, sticks to vertical surfaces, the head and vertical edge of the masonry unit, easily extrudes from joints without dropping or smearing, supports the masonry unit without excessive shifting or repositioning, easily compresses using a concave joiner, and maintains these qualities a significant period of time, meaning it has a good board life. We have covered the basics of the mortar itself. Now we move on to the requirements for mortar joints. What is a full head and bed joint? That depends. On hollow units, a full bed joint on a hollow unit covers the depth of each face shell to the height of the bed joint, typically 3/8 of an inch, the full length of the unit. A full head joint on a hollow unit covers the depth of each face shell to the width of the head joint, typically 3/8 of an inch wide, the full height of the unit. Further, all web should be fully mortared the depth of the unit to the height of the bed joint, typically 3/8 of an inch high, in all piers, columns, and pilasters, and, when necessary, to confine grout or insulation in the vertical cores. Ensure that vertical cells to be grouted are aligned and unobstructed openings for grout are provided. Grout and reinforcing will be covered in a later learning module. Solid units are treated differently from hollow units. Is this a solid unit? Or this? Or this? Let's start with a definition of what a solid unit is. A solid unit is a unit with net cross-sectional area of 75% or more of its gross cross-sectional area when measured on every parallel plane to the surface containing voids. In short, if the area of the unit, looking from above, is 25% or less of hollow space, it's a solid unit. All of these are solid units. With solid units, there are a few different rules. Place mortar so that the bed and head joints are fully mortared. A full head joint on a solid unit covers the depth of the unit to the width of the head joint, typically 3/8 of an inch wide, the full height of the unit. A full bed joint on a solid unit covers the depth of each face shell, plus any solid portion of the web material, to the height of the bed joint, typically 3/8 of an inch, the full length of the unit. The code requires that all holes that are not specified to be in the mortar joint be filled, below grade as well as exposed masonry. Unless a different joint style is specified, the code requires that all joints be tooled with a round joiner when mortar is not thumbprint hard. When not indicated otherwise, strike the joints with a concave joiner. This applies to backup assemblies and other locations where the finished surface will not be exposed. The code requires that any mortar protrusions into hollow cells over 1/2 inch be removed if the cell is to be grouted. Grout placement requirements from building code assume that cells be grouted are reasonably clear of obstructions. Removal of mortar protrusions over 1/2 inch helps to prevent voids in the grouted cells. The code does not allow head joints to be filled by slushing them with mortar. Slushing is the process of shaking or throwing mortar off of a trowel into the top of a head joint in an attempt to fill it. Slushing will not create a good head joint. First of all, the mortar is not placed under compression and is thus unlikely to develop adequate contact for bond. Also, in shaking or throwing the mortar off the trowel may be struck against the top of the brick. The impact of the trowel on the brick can break the mortar bond, resulting in an increased water penetration and reduced wall strength. Form head joints by placing mortar on the end of the brick and shoving the unit into position in the wall. Do not deeply furrow bed joints, and head joints should be formed by shoving the mortar tight to the adjoining unit. Workmanship has a substantial effect on strength and bond. The time lapse between spreading mortar and placing masonry unit should be kept to a minimum because the flow will be reduced through suction of the unit on which it is placed. This time lapse should normally not exceed 1 minute. Reduce this time lapse for hot, dry, and windy conditions or with the use of highly absorptive masonry units. If excessive time elapses before a unit is placed on the mortar, bond will be reduced. The mason should not tap, realign, or otherwise move units after initial placement, leveling, and alignment. Movement disrupts the bond between the unit and the mortar, after which the mortar will not reestablish bond with the masonry units. For this reason, building code requires that disturbed units be removed and reset using fresh mortar. Collar joints. Unless otherwise required by the project documents, collar joints less than 3/4 of an inch wide must be filled with mortar as the work progresses. What are the grounds for rejecting mortar joints in hollow masonry and in solid masonry? Any end joint that is not the full thickness of the face shell of a hollow unit, or any end joint that is not the full thickness of a solid unit, the full joint length, is grounds for rejection. Any bed joint that is not the full thickness of the face shell of a hollow unit, or any bed joint that does not cover the solid portion of the full thickness of a solid unit, the full joint height, is grounds for rejection. Joints with holes in them are ground for rejection. Those that think it's okay to leave joints unfilled because everyone does it should know that the courts don't agree. Deep furrowed bed joints are grounds for rejection. Piers, pilasters, and columns without crosswebs are grounds for rejection. Untooled joints, flush-struck joints, rake joints, etc., unless specifically required, are grounds for rejection. Strike out the joints with a concave joiner unless it is specified not to. Unstruck joints, when not indicated, are potential grounds for rejection, even when the work is hidden. Tolerances of mortar joints. The most basic tolerance contribution in masonry wall construction is the variation in mortar joint thickness. The tolerances of the code are based on specified mortar joint thicknesses of 3/8 of an inch for conventional masonry. In clay, concrete, and stone masonry, the mortar bed joint thickness is permitted to vary no more than plus or minus 1/8 of an inch. If the specified thickness was 3/8 of an inch, permissible mortar bed joint thickness would range from 1/4 to 1/2 inch. In clay, concrete, or stone masonry, head joint thickness is permitted to vary from the specified value by minus 1/4 of an inch and plus 3/8 of an inch. When the specified thickness is 3/8 of an inch, head joints must have a thickness between 1/8 of an inch and 3/4 of an inch. The mortar tolerances established by the code are to assure minimal structural performance. Be aware that a masonry job site sample panel is required by code for many types of structures. The purpose of the job site sample panel is to establish both the structural and visual standard of quality. Because the job site sample panel is a visual reference of what the mason agrees to provide, it is important that the mortar joint tolerances of the sample panel be representative of the actual construction. Sample panels will be covered in their entirety in a different module. Tolerances in foundations. The starting mortar bed joint on the foundation is required to be between 1/4 of an inch and 3/4 of an inch thick, which translates to a tolerance of minus 1/8 of an inch and plus 3/8 of an inch, based on a specified 3/8 inch joint. However, the top of the foundation is permitted to vary from level by plus or minus 1/2 of an inch. This difference in permitted tolerances is incompatible with the levelness requirements for the overlying masonry. When the foundation is too low, more than 3/8 of an inch, the first course of the foundation must be grouted solid. If that is the case, The initial bed joint thickness is permitted to be as great as 1¼ inches, which translates to a mortared bed joint of 3/8 of an inch plus 7/8 of an inch tolerance. Joint reinforcement in bed joints. It is generally acceptable to lay joint reinforcement directly on top of the masonry course. Mortar is then spread over the wire and face shell or unit in one operation. Due to irregularities in the masonry and the wire, mortar surrounds the wire and bonds the components of the assemblage. Joint reinforcement should not be placed between thin layers of bed joint mortar, since thin layers of mortar have a tendency to dry out and lose bond to the masonry or between the thin layers. Placing joint reinforcement on top of freshly laid bed joint is also not recommended, since this procedure results in voids between the bed joint and the overlying unit. Placement, positioning, and lap requirements for joint reinforcing will be covered in a later module. Mortar joint appearance has a large impact on the perceived quality of the installation. A sample panel should be present on every project. As a mason, the accepted sample panel should be used to determine the standard of appearance for striking, mortar color, and alignment of the finished masonry. Colored mortar. The texture and color of finished mortar joint are determined by properties of component mortar materials, preparation of the mortar, workmanship, curing conditions, cleaning procedures, and environmental factors. It is important that the mason understand these relationships in order to control the texture and color of the mortar joints. In this case, the bottom mortar joint was tooled immediately after placement of the unit. Remaining mortar joints were tooled at progressively greater time intervals and thus stiffer consistency. The relationship between mortar consistency when tooled and mortar color is quite apparent. Tooling white cement mortar with metal tools may darken the joint. A glass or plastic joint tool should be considered. The effect of tooling on the appearance of a mortar joint is dependent on the type of joiner used and the stiffness of the mortar at the time it is tooled. Tooling a mortar when it is highly plastic or flowable will tend to pull high water content paste to the surface, resulting in a porous, light-colored joint surface. Sometimes units are laid almost up to quitting time, and the units are tooled too early. Tooling the joint while the mortar is very plastic does not provide the same degree of compaction. Proper compaction is needed to provide good resistance to water penetration. Joints that were tooled early often have multiple ridges on the surface of the mortar parallel to the direction of the tool. Ridges form as mortar sticks to the tool. If the mortar is allowed to become stiff before tooling, the joint surface will not readily yield to the pressure of the joiner, and friction developing between the metal joiner and the mortar joint will result in a dark, streaked surface. Joints are not properly compacted if tooled when they are too stiff. These joints must be aggressively worked and often have a darker appearance in the completed wall. When mortar joints are tooled at thumbprint hard, which is the proper consistency, the surface of the mortar joint is compacted, and a uniform appearance consistent with the body of the mortar is achieved. An additional item to be aware of is the effects of cold and hot weather construction on mortar joints. Weather conditions during construction may affect the performance of masonry structures. Precautions must be taken during both cold and hot weather conditions to assure high-quality construction. Requirements for cold and hot weather construction will be outlined in a later learning module. Cleaning and mortar joints. Actual cleaning of masonry will be covered under a later module, but it should be kept in mind that the least amount of cleaning with the least aggressive method is the ultimate goal. Prevention of staining will minimize the effort required in cleaning, which can impact color consistency of mortar joints. Minimize mortar droppings and smears on the face of the masonry. Avoid laying concrete masonry units with wet surface areas where mortar will smear. Roll back plank at the end of the day to minimize smearing and staining. Ensure the walls are covered when not under construction. Careful workmanship will minimize the impact of cleaning on potential damage to the joints. What are the consequences of rejected work? Tear it down. Work that does not comply with the building code will cost the mason contractor money, reputation, and anxiety. Knowing the code requirements of acceptable mortar joints and implementing them on the job site ensures that you, as a mason, are doing your best to help your employer remain profitable and that your work is accepted by the designers, building officials, and owners. Skilled masons, professionally installing work in compliance with the building code, can expect a high degree of public trust. If designers lose confidence in the quality of masonry, they are unlikely to design with masonry in the future. Architects and engineers' concern about poor masonry craftsmanship is a significant deterrent to the greater use of masonry. Wall leaks are not usually due to poor bond strength, but rather to poor contact surface between the unit and mortar. The key to providing strong, durable masonry depends more upon workmanship than any other single factor. Workmanship affects water permeance of masonry more than any other factor, and water causes most building problems. 90% of masonry problems I investigate are related to leaks, most of which occur through hairline cracks between mortar and the brick. By keeping in mind the building code requirements, you, as a mason, can ensure that job site problems that can stop projects are minimized. Your care and knowledge will ensure that masonry will continue to be the premier building system in our community.